Number 7, it's important that we learn how to do a tree diagram for 7. Okay? A tree diagram is a great tool when you have a question where you have a lot of conditional probabilities that are disjointed, meaning that you don't have any overlapping sections. If you had parts that were overlapping, like question number 5, a Venn diagram is always better for your jointed outcomes. In this case, we have disjointed outcomes, and so that makes a perfect problem to use a tree diagram. I'm going to draw mine horizontally, so we're just going to start here, right? A tree diagram is a way for you to list out the possible outcomes, right? In this example, it says in the problem, all bags entering research facility are screened. 97% of the bags that contain forbidden material trigger an alarm. 15% of the bags that do not contain forbidden material also trigger the alarm. If 1 out of every 1,000 bags entering the building contains forbidden material, what is the probability that a bag that triggers the alarm will actually contain forbidden material? You got all that?
It's a lot.
So the first thing we have to do is determine what are the 2 events that are taking place.
Non-forbidden material and forbidden material.
The bag either has material being placed in it or not. And the other thing is, it will either trigger the alarm or it does not. Right? Which one happens first?
Trigger the alarm.
So I got to put the alarm goes off or not, and then I'm going to put the material in the bag?
No. You're going to put the material in the bag, but...
There we go. The bag, we have to put the stuff in the bag first, right? Or not. And then when I go through the alarm, or when I go through the security checkpoint, then the alarm will either go off or not. So when I write out my tree diagram, placing them in the correct order is extremely important. And so the first thing that can happen is you either have the forbidden material or you do not have the forbidden material, right? So the question is, we need to find out these probabilities. Obviously, these are very much a disjointed outcome. You can't have forbidden material and not have it. These are opposite actions. Also, they're complementary. If I know the probability of one of them, since they are literally complementary, there is no other outcome, they have to add up to 1. And that's really important about a tree diagram. When you split a stem here like this, no matter how many ways I split it, and it can be more than just 2, when I add the probabilities of those splits, they must always add up to 1. If they don't, I'm missing something or I've got the probabilities wrong, right? It's a lot like that probability distribution table we were looking at. What's the probability of finding forbidden material in any bag?
0.97.
1 out of every 1,000.
It's 1 out of 1,000. Reading comprehension, pretty big deal here. You can't just look at the numbers and pick the first one you see. There's a whole bunch of numbers there, okay? We joke about that, but that happens all the time. People that don't take this seriously and don't learn this task, I would say this is one of the biggest tools to use in this chapter for this kind of problem. This is going to show up a lot in this worksheet, so make sure you pay attention. Right, so it's 0.001, 1 out of 1,000. What's the probability that we do not find the material in the bag?
0.99.
It's just 1 minus that value, right? So 0.999, right? And so if we kind of keep going, what happens next?
It either sets off the alarm or not.
Yeah, we have the alarm going off or no alarm, right? Alarm or no alarm. What probability do I have now? If it has forbidden material in it, what's the chance the alarm is going to go off? Notice how we said that. I have to take a path. If I choose a certain path, if I choose the forbidden material path, then what's the chance the alarm goes off? This is always if-then kind of situations because it's conditional. Because the probabilities will change based on the path that I take. So when we are kind of following this path down, I'm literally saying if it has forbidden material, the alarm goes off what percent of the time, and you are correct, it is 97%. That would mean there's a 0.03, not 3, not 0.3, but 0.03. 0.3 is 30%. I see that mistake a lot. What about if you don't have forbidden material? What's the chance the alarm goes off?
0.15.
Good. 0.15, and then, of course, 0.85 would be here. So this is my tree diagram. I only have two different events. And so if I follow the path down, it's kind of saying and, right? The forbidden material and the alarm goes off. So if I were to kind of write down the outcomes here, we would say this is the probability of having forbidden material and an alarm going off. This one would be what?
0.97.
And no alarm going off, right? This one would be the probability of no forbidden material and an alarm going off. The last one would be the probability of no forbidden material and no alarm. That's kind of like what you would expect the majority of the time to happen, right? And so this is, and here we're dealing with and. The formula for and is the probability of A times the probability of B, given that A has already happened. Well, the good news is that these numbers are exactly what I have for that. So it's literally, I'm going to multiply down the path. Now, I don't know that I need to do all of those, right? But what do I need? So if we go back and it says, what is the probability that a bag that triggers the alarm will actually contain forbidden material? How do we write this out symbolically? The probability of what? Given that what?
Of alarm given that
A bag with forbidden material.
We know what's the probability that it has forbidden material in the bag?
given triggers the alarm.
Given that the alarm's going off. That's what that last sentence says. Assuming the alarm is going off, what percentage of the time does it actually have forbidden material in the bag? Okay, so if I look up my conditional probability formula that we wrote down yesterday, I would say this is the probability of having forbidden material and an alarm divided by the probability of the condition, which would be alarm. Are there any questions about how we kind of got to that stage? Tree diagram helps me to organize all the information to get it right. If I don't know the actual question, if I don't know this, I'm really just, I'm stabbing in the dark. I'm just trying to get some numbers and I don't know where to go with that. So being able to read that last question and really extract out those crucial elements, or like what the question's saying, that's really important. Cece?
Probability of the alarm. Do you multiply? Is that where you multiply 0.97 and 0.15?
So let's kind of walk through it. I can see, first of all, that first part, forbidden material and alarm, I see that right there.
We already have it.
So that's awesome, right? Let's figure that one out. If we multiply 0.001 times 0.97, we're essentially taking a path and following it down and multiplying all the values together, right?
We got 9.7.
That's 0.00097. 9.7 times 10 to the negative fourth.
Oh.
Learn how to use your scientific notation in your calculator. Once you go past 4 decimal places, it automatically converts into scientific notation. Just move the decimal to the left. The number of times is in the exponent. Okay?
Wait.
Now,
Wait.
where's the alarm going off? Like where in my tree diagram, where is the alarm happening? Well, obviously it's happening here, right? Where else?
What is the? I'm so lost.
Right here. Go ahead.
What is the 0.0097?
That's the probability that the forbidden material is in the bag and the alarm is going off. That right there. That times this equals 0.00.
That is the.
Just the top part.
That's the top of the fraction.
I'd like to know, so that's part of the time the alarm's going off. We also determined that the alarm goes off in this one too. So what's the probability the alarm is going to go off? Well, we're going to have to take that 0.999 times the 0.15. And we can figure this out to be 0.14985. So the alarm can go off when it has forbidden material and when it doesn't have forbidden material, right? And so if we were to find out just the probability of the alarm going off, right, what's this? How do I find the probability of the alarm?
Do you multiply those two things?
By multiplying, you're implying that those are and they can happen at the same time. The alarm can go off when you have forbidden material in the bag and when you do not have forbidden material in the bag, right? Because it's an or question. Because you either have forbidden material in the bag or you don't. Those two things cannot be simultaneous.
So what do you add?
The two probabilities.
There's 4 probabilities.
So, no, there's not. Well, there are 4, but we only care about the ones when the alarm is going off, right?
Oh,
So we've the ones we 2 calculated to point
that's,
0.
it's more than 1.
That's right.
Is it allowed to be more than 1?
There's 2 times, right? The alarm can go off when you have forbidden material in the bag, or the alarm can go off when there's no forbidden material in the bag.
But it's going to go off more than 100% of the time.
No, it won't.
That makes sense.
That's equal to 0.15, what is that? Plus 0.082. So this is the probability of when the alarm is going to go off just in general. Because I found every time it went off in my tree diagram. And since between the branches we have to add the values because it's this one or it could be this one or it can happen here or it can happen there.
I thought
It-
we were doing 0.97, 0.15.
If I added all, no, you have to multiply down the branch before you can do that. If I added all 4 of these probabilities, if I had calculated them, what do you think they would add up to?
1.
Why?
Because it has to.
Because this is every single possible outcome. One of these outcomes is going to happen, right? This is the sample space. So when I add up all 4 of these numbers, it will add up to 1, or I'm wrong in some category, right? Or somewhere along the lines. We don't really care about the ones where the alarm isn't going off, right? My question wasn't about those. So I did find the value of when it was going off in general, right? So we have now all the numbers we need in order to calculate the total probability. So this is going to be 0.00097 divided by 0.15082. That's equal to 0.0064. And that becomes answer choice E.
I got it right.
Be careful, getting it right by luck is as good as getting it wrong.
It was not luck.
We'll see.
Is number 8 a trick question or is it just easy?
On question 16, we have a two-way table, and we have a question that wants to determine whether or not these events are independent, right? Are being type O blood and being type A blood independent events? We have a couple of options, right? Let me just kind of refresh our memory on what is our rules, what do we have to justify independence or not, right? We know that the probability of A times the probability of B would be equal to the probability of A and B if they're independent. We also have a rule that says if the probability of A given that B occurs is equal to the probability of just A by itself, meaning the fact that B happened didn't change the probability, would also tell me that these events are independent. Right? Let's kind of define A in this problem. Let's let that be we'll let that be type A, and then B would be type B blood. Is that what it is? O. Okay, so I can kind of figure these out. Now, note that I have to find each one of these values separately to justify these rules. I can't multiply A and B together to get A and B, because then obviously I've made the assumption that they are independent. But I don't have to do that, right? So if we do, what's the probability of having type A blood? What do we know?
153 out of 390?
Yeah, so we have 153 people out of the total 390. What is the probability of having type O blood? Or that's going to be 183 out of 390. Now, if we know that these two things well, if we want to check, we can multiply them together. If we multiply these numbers together, right, 153 over 390 times 183 over 390, that should be equal, and that's a big question mark there, to the probability of having type O and type A blood. So where is that in the table? Where do you find the people that have type O and type A?
There isn't.
So what's the probability of having type O and type A?
0. I was gonna know.
Oh, so that's impossible. So the fact is you can't have type O and type A. So it is definitely an impossibility. So it doesn't matter. This is not true because 153 times, oh, that whole fraction over there, this is equal to 0.184, which we clearly knew wasn't going to be equal to 0. The fact is we know that they are now definitely not independent. But I'm trying to find out which answer choice would be right. A says no. C also says no, right? So we can kind of eliminate all of these. These are crap. And my answer doesn't really justify either one of those things, right? Let's go the other route. We also know this formula right here, right? What's the probability of type A blood? Okay, well, type A, the probability of type A, if we write that as a percentage, is 0.47. That's important. Or type O, sorry, that's type O. Yeah, that's type O. The probability of having type O is equal to 0.47, which we call B, I guess, keep my letters the same. What's the probability of having type A given that you have type O? 0.
But C is stupid because
It is.
80,
It is.
because you
It
can
is.
be
Yes,
okay.
right.
Okay.
But I don't want to just, I don't want to choose an answer by default in this situation. I want you to understand why this answer is what it is. Because sometimes you do have a choice that may make sense. We have to make sure that we understand the question. But answer A, of course, says no. The probability of type that a patient is type O is 0.47. We found that out. But the probability that a person is type O given that they're type A is 0. So we are using that rule, and that rule did not come true. So it's false. Therefore, we have proven it to be not independent.